Well, greetings, mathletes, and welcome back. Today we're going to be taking a look at inequalities again, and we're going to expand a little bit on what we looked at last time. Because sometimes there's certain situations where the way that we presented our answers in the last lecture aren't adequate. So what we're going to end up doing is learning a little bit about that new situation, and it's kind of hard to describe, so I'll just show it to you in a minute here. And then we're going to also take a look at a new notation for stuff we do already know how to do. So let's go ahead and take a look at what we got here. Okay, so before, what we were doing, let's make sure I have an actual pen on here. Let's see here. We were looking at inequalities like this. And I'm just going to make up one of these three-sided ones. Let's say we have from 1 to x up to, let's put an equal to on that one, and we'll leave it off of this one, and we'll just make it 5. Okay, so we looked at these things before. And if we were going to graph this, it would look like, well, let's try that again. Right, if we were going to graph this, we'd have a 0 here. Let's see, we'll just say 3 is there. This is less than, it does not have the equal to, so it has a round bracket. And we go to the left. Let me switch colors, that'll make that a little nicer. Right, and then we color everything to the left. Okay, and we use that round bracket. If we were going to write the interval for this, well, that interval starts at negative infinity, goes all the way up to 3. It has a round bracket on 3, and infinities always get round brackets because you can never reach them, right? Infinity is not even a number. It's a destination you can't get to. Okay, now if we went ahead and switched this, and we look at this one here, this one does have the equal to, so same kind of business, 0, 3, but with the equal to, we put the square bracket on it and then color it here. Right? So it's everything to the left of 3. This time, 3 itself is part of the solution, and that's actually what that square bracket means. It means 3 is a solution. The round bracket means 3 is not a solution. So you can get as close as you want to 3, but you can't hit 3. You get 2.9, 2.99, 2.99999. As long as you don't hit 3, it's still a solution. But as soon as you hit it, it's gone. So same thing here now. If we're going to use the interval notation, it goes from negative infinity up to 3 again, but this time it uses the square bracket to indicate that 3 is part of the solution. Then over here, let's say 0's there, 1's there, and we'll go all the way up to 5. Excuse me. Now, with this one, let's see here. This is everything between 1 and 5. I know that much, so it's going to be all of this stuff, and I'm just going to double stamp the line here so it's nice and solid. Okay, and then since we go from 1 to 5, this one has an equal to, so that means it includes the 1. So we have a square bracket on this end. And this one does not include the 5, so it has a round bracket here. And so our interval notation would be from 1 to 5, square bracket on the 1, round bracket on the 5. Right? Okay, so now here's where the change comes in. Okay, these are all real number solutions. So let's say I want to write that somewhere. These guys here, these are real numbers. Right? And the reason we say real numbers, we're restricting our solutions to real numbers, is because everything in between here is also a solution. Right? Anything that's shaded by this line is a solution. These are called continuous intervals. Right? And that's because there's no breaks. There's no breaks in the solution. Right? In everything between 1 and 5, without exception, is one of the solutions. Now, what changes is sometimes you are given a set of integers to work with, right? So some of these say, solve this inequality, and I'm just going to keep using these three inequalities so we can use them as examples here. Solve this inequality for x is equal to 0, 1, 2, 3, 4, 5, and I'm going to do all of these with this. 6, 7, 8, and 9. Okay, and this list could, I mean, it doesn't have to be everything from 0 to 9. You could have 10s in there, you could have other stuff, but this is just what I'm picking for this particular example. And what that means is the only things that are allowed to be answers are things that are on this list. Okay, so when I look at this, x is less than 3, the question is, which one of these x's is less than 3? Right? And so if I was going to graph this on a number line, right, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm going to write these into. Okay. Now this would this is a terribly drawn number line, so forgive me for this. Your number lines and your homework and stuff look a lot nicer. In any case, basically we want to know from this list how many things which things satisfy this inequality. So which things are less than 3? Well, let's see here. 0 is, so we'll mark that. You notice I'm not making a line, I'm making a point, right? Because 0 is a point. There's nothing on either side of it. It's sitting there by itself. Let's see, 1 is less than 3. 2 is less than 3. 3 is not less than 3. So that ends up being my full graph of this solution. Basically, what you end up doing is you look at the inequality and you figure out which things on the list work for the inequality. So let's look at the next one here. So let's see, this one is x is less than 3. So I'm going to shorten the things I put on here this time because we know it's going to be pretty similar. Oof. Boy, my tick marks are bad. Okay, and it does, it keeps going until 9 or what have you. Now, if we look at this list of x's, for x is less than or equal to 3. Well, let's see here. 0 works, just like before. 1 works, just like before. 1 is less than 3. 2 works. 2 is less than 3. 3, well, it says less than or equal to 3. And the 3 is equal to 3, so that qualifies. So this time we include the 3 when we graph it. Right? So if it's less than, then it has to be less than. But if it's less than or equal to, then the number itself is game to put in here. All right, so now let's go ahead and look at the next one here. And I'm going to put a few more tick marks on this one. 0. Okay, so we're looking at this inequality. And basically, and keep in mind, we're still using this list. I just don't want to keep rewriting lists over and over again. That's why we're reusing it. So yeah, this is our list. Let's see here, which things fall between 1 and 5, and the 1 is inclusive, meaning that 1 is a solution as well. So let's see here, 0 doesn't work, 1 works, so I'll mark that. 2 works, 3 works, 4 works, 5 is not less than 5. 5 is equal to 5. So I can't mark 5. It's just the 4. And so that graph ends up looking like this. Right? So when you have a list of numbers there, what it's asking you is which numbers on this list are solutions to the inequality. Now, the reason that we do this for stats is there's a lot of times when we use an inequality to estimate something. But the values that the inequality can assume happen to be whole numbers, like you're trying to estimate the number of people for something. Well, you're not going to have 3.1 people, right? You're going to have 3 people, or you're going to have 4 people, and it just depends on what the situation warrants. But so there are situations where you have set numbers and you can't have anything in between them. And so, just for vocabulary's sake, when you have something like this, these x values are what's called discrete. Right? And discrete means that you can pick them out as individuals and there's nothing on either side of them. And discrete is in comparison with continuous that I used before. Continuous is when it's the whole line and the line is solid. Discrete is when they're separated points. Okay, now your book doesn't hang a whole lot on that vocabulary, but it is good vocabulary to know because it does come up a lot in math, particularly in statistics. You need to know whether your variable is a discrete variable or a continuous variable. It makes a difference which formula you use sometimes. Okay, so let's go ahead and clear that off. Now, we want to take a look at a new type of statement and apply this new knowledge to that new type of statement also. Okay, so let's suppose we have what's called an OR statement. So we have, let's see, x, there it is. Let's say x is less than 2 or x is greater than or equal to 5. Okay, now what an OR statement means is that if either one of these are satisfied, then it's a solution. So with an AND statement, it has to be true for both of them, right? And we actually write AND statements as a 3-sided inequality. So I'm not going to really spend a lot of time on the AND statements because we have talked about the 3-sided inequalities, but we will visit those before we're done today. But looking at these OR statements, if I want to graph this over the real numbers, right? So if I want to look at this over the reals, the way this ends up panning out is, let's see here, I'm going to put 0 over here, 1, 2, 3, 4, 5, 6, 7. Okay, so 1, 2, 3, 4, 5, 6, 7. Oh, suddenly my graphs look better. Okay. In any case, basically what you do is you just graph both inequalities, right? You put them both right there on the same graph. So x is less than 2 should look like this. Right? It's just a round bracket pointed to the left at 2. X is greater than or equal to 5. It has the equal to, so I put a square bracket on this, and then it's everything to the right. And so the graph of this particular compound inequality, and it's called compound because there's 2 inequality statements here, the graph looks just like this. It's basically you graph this thing, and then you graph this thing. That's it. Now, if you are going to use the interval notation for this, there's one additional thing we have to use for the notation. Basically, you just write down both intervals. Okay, so the first interval here goes from -infinity up to 2, and it's a round bracket at 2. The other interval starts at 5 with a square bracket and goes up to +infinity. Now, we want to indicate that these 2 solutions are part of the same solution, or these 2 intervals are part of the same solution. So what we do is we put a union between them. And you notice that is not this. It doesn't have a tail on it. It is this, right? So that's wrong. This is right, right? And what it means is union. It's basically glue, right? It takes these 2 pieces and it glues them together so they're the same set, right? Even though there's a break in the set, it makes them the same set. So that's your solution, is basically the union of these 2 intervals. Now, suppose we were doing this in a discrete fashion also, though. So it said graph x is less than 2 or x is greater than 5. Oops, let's switch colors. well, let's erase it first. And turn on the pen. There we go. For x is equal to negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I got a little too close to the edge there. I hit the scroll. Okay, let's just stop it at 8. There's not room for 9. And just keep in mind, you get a different list every time. In any case, if I want to take this and adapt it to solutions over this set, basically the solutions, the discrete solutions, are x is equal to, well, let's just walk through these one at a time. We're going to pick each number and decide whether it satisfies one of these inequalities. Negative 1 satisfies the first one, so that's a solution. 0 is less than 2, so that satisfies the solution, or satisfies the condition. 1 is less than 2, so that satisfies the condition. 2 is not less than 2, right? So we can't write that down. So we stop there. Now, we keep going through this list. So 2 doesn't work, 3 doesn't work, 4 doesn't work. 5 satisfies this one now, though, because 5 is greater than or equal to 5. So we'll put 5 down now. 6 is greater than or equal to 5. 7 is greater than or equal to 5. And 8 is greater than or equal to 5. And so in the discrete case, right, the case where you're limited to these values for x, these are your solutions, right? So it's really just, you're looking at this list and you're asking yourself which of these numbers would be covered by one of these arrows, right? By one of these lines here. And these are the numbers that would be. So when you're given a discrete list like this, what you're doing is you're going through the list and you're testing each number one at a time to see if it satisfies the condition we're given. Okay, so I want to have you guys try one of these real quick, just to make sure, just to convince yourself that you know this. So let's say, oh yeah, that whole pen thing, it's still eluding me. Okay, so let's, oh, there we go. Let's do this. There we go. I think we got it now. Okay, so let's try this one more time. I got the pen on and everything. So we want to graph and write the interval for x is less than or equal to 0, or x is greater than 3. So first I want you to do this for the reals, and then for x is equal to, let's do negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6. Ugh, that's just written horribly. Take a penmanship course or something. Okay, so see what you can do. You need to graph it, write it as an interval, and then graph it for the discrete case. Okay, so go ahead and pause it here and give it a shot. All right, so let's go ahead and take a look. We'll look at the case for the real numbers first. Because you notice here, we're not doing any computation. All we're doing is presenting the answer. So we're reinterpreting an answer is all we're doing right now. So first of all, let's go ahead and look at for the reals. We'll start with a graph. And looking at this, I'm just going to do this real quickly. That should be, let's see, it's less than or equal to 0 or greater than 3. And you notice how I'm doing this real quick here. Okay, so we have that. That's our graph for real numbers. And then if we're using real numbers, we need to talk about the interval. So the interval would be negative infinity up to 0. And I want to union that with, oops, I want a round bracket here at 3, and 3 goes up to infinity, right? Then, for the discrete case, I want to take a look at this thing. So all this was what part A looks like, and then part B is for these numbers. So basically, we just want to check these numbers one at a time and see which ones satisfy at least one of these two things. So let's see here. Oh, negative 2 is less than 0. Negative 1 is less than 0. Oh, and then it's a less than or equal to. So when I get to 0, 0 is less than or equal to 0. 1 doesn't satisfy either inequality. 2 doesn't satisfy either inequality. 3, oh, nope, it doesn't satisfy. It doesn't have an equal to on here, right? Because 3 isn't greater than 3. It's equal to 3. So that means 4, 5, and 6 are the only other numbers. Okay, excellent. All right. So now the last thing I want to talk about here is what's called plus minus notation. Oh, I keep doing that. Try this again. And the way this works, this only works for stuff that looks like this. Okay, you notice there are no equal to's on here whatsoever. These are strictly less than. And it's a compound inequality. It's one of our three-sided inequalities. Okay, so this is the only time you can use plus minus notation. So here's how it works. If I look at this, I'm going to actually start with numbers because I think it'll be easier to see if we actually pick numbers here. Let's say I have an inequality, 2 is less than x is less than 6. And so if I graph this thing on a number line, ooh, that's not what I wanted to do. Try that again. Let's put the 0 over here. So that's 2, 3, 4, 5, 6, right? If I were to graph this thing, it would look like this. I'd have round brackets on both ends, 2 and at 6, and go from here to here, right? Well, here's the thing. A lot of the time, how do I want to explain this? One of the ways that this can be broken up, right, is by its midpoint, and this distance to the ends from the midpoint. So how far is it? It's almost like a radius, really. So how far is it from the midpoint to the edge? We know it's the same distance either way. Okay, so what we would like to do is to first find the midpoint. Now, first of all, we can look at this. If that's 2 and that's 6, this midpoint is 4, right? You can clearly see there are 2 units on either side of this. So we start with 4, and we want to point out how far away from 4 the endpoints are. Well, we know that if I get to this endpoint, I have to add 2 to the 4. To get to this endpoint on the lower end, I have to subtract 2 from 4. So here's the plus minus notation. This interval from 2 to 6 can also be written as 4 plus or minus 2. Okay, so what this is a way of listing both endpoints at the same time. Excuse me. Okay, now there's going to be a question here as to how to find the midpoint and how to find the distance to the edge. Now there's a few different ways of doing it, but there are formulas for it. Right? It actually turns out if you want to know the midpoint between two numbers, you average those two numbers. So between A and B, if I want the midpoint, in fact, let me put this in black. Let's try it again. Okay, if I want the midpoint, I average the endpoints. So that means I add A plus B and divide it by 2. Right? Notice over here it would work. That would be 2 plus 6 divided by 2, which is 8 over 2, which is 4. And that's my midpoint, right? We've already done this visually. So if I average the two of them and divide it by 2, that's my midpoint. Now, and then there's this matter of this distance here. Now, your book calls this distance D. So that's plus D, and that's minus D. D is the difference between the endpoints, because if I take 6 and I subtract 2, right, that gives me 4, and that tells me how long my interval is. So if you want to know how long something is, you subtract the two endpoints. So that's 6 minus 2, but you'll notice it's only half of that interval length. So it, 6 minus 2. B minus A is what I meant to write. So it's B minus A, and then I want half of that, so that's over 2. Okay, so here's what I want to do. I want to walk back through this exact same problem, but this time we'll use the formulas. Let's see if I can erase this. Whee. Okay, got pen back on. All right, so we had an interval from 2 to 6. And we want the plus minus notation, right? So what we need first is the midpoint, because these are always going to be written, by the way. It's the midpoint plus or minus D, right? So as long as we can find both of these things, we're good. So I want my midpoint first. The midpoint is the average of the two endpoints. 6 plus 2 over 2. That's 8 over 2, which is 4. You did it again. Give someone a seizure doing this. Let's try it again. Okay, so that's 4. So my midpoint is 4. Now I need D. D is B minus A, so it's 6 minus 2 over 2, which is 4 over 2, which is 2. So what that means is my plus minus notation here is going to be 4 plus or minus 2. Now, what's kind of interesting about this, you actually see this stuff all the time. This is an election year. I'm sure if you've watched some political ads, you've heard things about approval numbers or stuff from polls, who's ahead in the presidency, and you'll see, candidate X has 48% of the vote, plus or minus 2%, right? That's the notation we're actually looking at here, right? We had 4 plus or minus 2. What this means now is it does not mean that that this is 48% and you have a 2% chance of being off. I think that's how most people end up reading these. What it means is that the actual percentage, right? If that's 48, if I count down to 46 and up to 50, what it's saying is the actual percentage is probably somewhere in here between these two numbers. It is not saying that it's 48. It's saying that it's probably within 2 units of 48. Okay, so this is one of the things about statistics. In fact, when you take statistics, you'll find out how they come up with these numbers in the first place, right? You actually get to see all those formulas and stuff. It's quite interesting. They're called confidence intervals. But yeah, we see this quite often. Now, this actually leads us directly into the next thing we need to do, which is to be able to construct the interval from the plus minus notation. And we just did that, right? You take the midpoint, you subtract 2 for the lower end, and you add 2 for the upper end. So, looking at this, we could actually walk backwards to our original inequality, but I think I'd rather look at a fresh example. So make sure you have these formulas down, because these are going to dictate everything, right, if you want to convert this stuff. So let's go ahead and collect that. We'll do that, turn this back on, and okay. So let's write interval notation and graph, right? You really don't have to do it in any particular order. But if you're handed something like, I don't know, 6, let's make it fun. 16.1 plus or minus 3.4. Okay, so the first thing we need to do is figure out our interval. Right, so the lower end of the interval, and we can actually just write this out, is the one that uses subtraction, right? Because if you subtract, you go down to the lower end. So this lower end is 16.1 minus 3.4. The upper end is 16.1 plus 3.4. So we just need to simplify these expressions now. So we pull out our handy dandy calculators, and we got 16.1 minus 3.4. That gives me 12.7. And then 16.1 plus 3.4, and we shouldn't need a calculator for that, that's 19.5. Right? And so this is the interval that we should be talking about. And if we're going to graph this thing, I'm just going to say 12.7 is right here, and 19.7 is up here, or 19.5 is up here, right? If we're going to graph it, we just need to make sure we find those endpoints, and then we can just graph it, right? So not much has changed after that, but it's a matter of just understanding this new notation, right? Okay, so that was actually the last thing that I wanted to talk to you guys about today. So we'll go ahead and wrap it up here. And so until next time, keep your pencils and your wits sharp.